Okay, we are going to talk about the central limit theorem. So this is a very, very important result which actually makes a lot of the statistics that we do possible. So it's kind of a result. It's a more advanced result where if you actually understood what it was, in general, it would be difficult to understand. So we're going to think of it like this. This is really just kind of one of the results of the central limit theorem. And this is how we're going to think of it. Okay? We're going to think the central limit theorem CLT. The central limit theorem is going to tell us when d of x bar is either normal or approximately normal. Okay, so the central limit theorem is going to tell us when the distribution of x bar is either normal or approximately normal. So there's two cases. Okay, the first case is when the population is normal. Okay, when the population is normal, the distribution of x bar will also be normal for any given sample size. And then in parentheses, and this will make more sense when we look at case 2, in parentheses I'm going to put even when n is less than 30. Okay, now right now that doesn't make sense, but it will in a moment. Okay, so the first case, when the original population is normal, so the population you're taking the samples out of, if that is normal, then your d of x bar is also going to be normal for any given sample size. So there's a sense in which it kind of inherits that from the population. It has the same shape as the shape of the population. Now here's the amazing thing about the central limit theorem. Okay, and what this says is when the population is not normal, we'll say when the population is not normal, and then in parentheses I'll say or is unknown, d of x bar will be approximately normal given that the sample size is sufficiently large. Okay, and our rule of thumb is n greater than or equal to 30. Okay, so basically the amazing thing is even if your population is not normal, as long as your samples are 30 or more, then you can assume that the distribution of x bar will be approximately normal. Okay, that's the way when you pull out all those samples and you start graphing them, even if the original population is not normal, the distribution of all the sample means is going to have a normal shape to it. It'll be approximately normal. And as n gets larger, so 30 is not a magic number. As n gets larger and larger, the distribution will become more and more normal. And they say, you know, mathematically, as n goes to infinity, then in the limit it becomes a normal distribution. It's just in real life, you know, your sample size cannot go to infinity because the population you're taking them out of is finite, right? So your sample size would never go to infinity. So that's just the mathematics behind it. But basically, if n is greater than or equal to 30, even if the original population is not normal, d of x bar will be approximately normal, as long as your samples are sufficiently large. And so we can make that assumption even for any population, even if we don't know anything about the shape of the population. As long as we got large enough samples, we can assume that the distribution of the sample means will be either normal or approximately normal, and that's going to allow us to make statistical inferences. Okay? And so let me just kind of show you, I'm going to draw a diagram here to just kind of help you understand kind of what's going on here. So let's say my original population here is not normal. So maybe we'll say it's actually, you know, it might have like 2 big humps like that. This is a bimodal population. So we'll say this is the original population. And it is not normal. It's very not normal. Okay, so the idea here is if you took out, let's say, your distribution of x bar had samples of size 5, then what you would see happen is maybe something like this, where these 2 peaks are less pronounced. Okay, so we'll say this is like d of x bar for n equals 5. Okay, and then let's say we took it out for n equals 10. Then maybe it might be something like this for n equals 10. Okay, so it's becoming even smoother here. And maybe for n equals 20, we'll say d of x bar for n equals 20, then maybe it becomes even smoother. Maybe it's just left skewed now. And then the idea here is by the time you get to 30, the shape of the distribution of sample means for samples of size 30 is going to be approximately normal. Okay, and it might not be exactly perfectly normal, but really any population, even the ones we call normal, are probably, you know, approximately normal anyway. So by the time you hit 30, pretty much any population is going to be approximately normal. Now 30 is not a magic number. Okay, it's a rule of thumb. And they use it in all intro to stats classes. And so usually you want your studies to have samples of 30 or more. Okay, but it's not a magic number. Let's say your distribution or your original population was maybe just a little left skewed. Then you could probably get away with samples of size 10. By that point, something like this would be approximately normal. Okay, so 30 is not a magic number. It's a rule of thumb. And as n increases, d of x bar becomes more normal. So if you take out a larger n, it's all the better. The d of x bar becomes more normal. Not only that, but the standard error shrinks down as well, and you have less sampling error. And so just overall, your results get better. So larger samples means better results, okay? And usually with a statistical study, they say you want to have at least 30 or more. But even larger, that's even better. So, okay, so that's the idea behind the central limit theorem. So with our last set of videos, we're going to do some examples and kind of show you how this comes into play.